How many people who are interested in taking the psych exam have not talked to Miss Evans? Shame. Shame.
You guys are gonna...
What are you waiting on? So what are you waiting on song? We're on page 121. This is a short section. So I'm going to kind of do this and then bleed on into the next section because the next section is longer reading. How do we know about the brain? Well, cut it. There's a lot of ways to figure out what's going on in the brain. First, you can study patients with damaged brains. There's all kinds of brain damage that occurs due to injury, due to stroke. Stroke is when you have a broken blood vessel in the brain and it cuts off oxygen to a part of the brain. And then you can see what's wrong with the individual and see what they can't do and then figure out what part of the brain does that thing. For instance, if they can't move anything in the left side of their body, if they can't move any of the left side muscles, and you notice there's been brain damage on the right side of the brain, you may then be able to conclude that the right side of the brain controls the muscles on the left side of the body, which we now know is true. Do you see what I'm saying? Sometimes the doctor or scientist create lesions. A lesion is a cut. You can go in there and cut part of the brain and see what happens. That's not a real experiment that you would want to be doing, but sometimes you have to cut the brain to get to a cancer or something that you have to remove, and you can see what happens. Have you ever heard of an operation called a lobotomy?
Yes, in fact. Those are fun.
A lobotomy is kind of an operation that used to be done more commonly, and when they had some crazy person that was
Crazy.
out of control and maybe doing a lot of damage to society, sometimes they would take a red-hot poker or a knife and they'd
Wiggle around.
shove it into his front of his brain. And they call that a lobotomy. And a lot of the times it killed the guy, and they were done with him anyway. They were going to do that anyway. Sometimes it made him better. And sometimes it changed the personality and all sorts of things. So we call those types of operations lobotomies, and they aren't done very often anymore. But it's something you used to hear about. And so that is a doctor/scientist created lesion, a lobotomy. There are lobotomies that are still done, but it's a lot more precise, and they aren't just randomly sticking stuff up there. They know where they're going.
So they do it. Nasal cavity.
Yeah, you can go through the nose. You might be able to go through the frontal bone. You have to drill holes and such. There are different ways to do it. Of course, you would put the person under anesthesia so they wouldn't feel any pain. An EEG is a brainwave recording. Look on the picture on page 121 in your book. See that guy? He's got a lot of electrodes on his head. We call that an EEG. And the electrodes that are taped to his head can pick up signals, electrical impulses that are happening inside his brain. And they put the electrodes in the proper location and let a computer record what's going on, and you can see what's happening down deep in the brain and kind of maybe get an idea of what's going on. Like, for instance, here's an example of EEG readings of a person in various stages of arousal, meaning various stages of sleep or wakefulness. So deep sleep, here's what the brain wave pattern looks like. Relaxed, here's what it looks like. So you could put an EEG on a guy, for instance, tell if he was asleep or not. Of course, you might be able to tell that just by looking, but sometimes you never know. You know, a guy laying there in a coma, what state is he really in? Is it more like deep sleep or is it more like relaxed? You know, who knows? You can get a reading from an EEG. So EEGs can be used for all sorts of things. Needle electrodes. Often during brain surgeries, they'll open up the skull and they'll use these needle electrodes and they'll touch the electrode to the brain itself. And that starts an electrical signal in the nerves that they touch. And for instance, if you touch one part, you might get an arm movement. And if you touch another part, the person might say that they are seeing lights. If you touch another part, the person might say they remember a song from their past. And so you can kind of make a map of what's what in the brain from using these needle electrodes. And they'll do this anytime they're going to go cut into the brain, maybe to remove a tumor or something like that. The brain surgeon will use those needle electrodes and they'll touch it, and the patient has to be awake for it. So they use a local anesthetic. And they touch this part of the brain and they say, "What are you feeling?" And the patient goes, "I'm hearing sounds." And they go, "Well, we don't want to cut there." "What are you feeling now?" And they go, "Oh," and they go, "Oh, we don't want to cut there." And they go, "How about here?" And the person goes, "I got nothing." The doctor says, "You sure? How about there? You can't feel anything? Nothing?" The person's like, "Nope." "All right, let's cut through there to get to the tumor." Isn't that interesting?
Wait, what if it's something they can't feel?
What's that?
What if it's something they can't feel? Wait, oh wait, my kid stopped working or something.
Yeah. Then that's a problem. But you know, the doctors do this, and usually they can find some place to go to get the tumor. The interesting thing is, it's not exactly the same in each person. So it differs a little from person to person. So you can't just have a chart of the brain and know that there's nothing here, we'll go in here. In each person, it's a little bit different. Kind of interesting. I've got video footage of that happening.
We can go back to the brain surgery to demonstrate the electrical nature of the nervous system. In addition to recording the brain's electrical activity, the surgeon will use another kind of electrode to introduce a small electric current into the patient's brain. In essence, he creates a nerve impulse that travels through her nervous system. The patient must be conscious to report the results of the doctor's probing. She feels little or no pain, for the brain has no pain receptors of its own. When you see her mouth open, it is because the doctor has stimulated an area of her brain that controls the mouth. She isn't moving it on her own.
Anything there?
The patient may feel a tingling sensation somewhere else on her body instead. The impulse could even cause the patient to see things that aren't there, or hear music. The effect depends on the site of the stimulation.
Isn't that interesting? What they'll often do is have the patient just start saying a series of numbers or letters. They'll say, start saying the alphabet. Usually they'll make it a little tougher than that, so the person has to think. And they'll say, say the alphabet backwards while he's probing, and the person will go, Z, Y, X. And then if he gets someplace and the person goes, then he knows he's hit, something involved in the speech or something involved in that. And so he can kind of hear while he's going. So, this is why they pay brain surgeons a lot, and brain surgeons go to school for a long time to learn how to do all this. That's a tough job. If you screw something up there, that can affect the person forever. Although it is possible for nerve cells to recover, most nerve cells don't grow very fast. And some never reproduce again. So if you lose brain cells, you're likely to not get them back or not get much of them back. A PET scan, PET stands for positron emission tomography. And what they do in a PET scan is they inject radioactive elements into your blood or into your body somehow. And one way they can check the brain is they can inject radioactive glucose. Glucose is a sugar that's used by the body for energy. And you know what organ in your body uses the most energy?
The brain.
Your brain. You'd think it's your muscles or something, but it's not. Your brain actually uses a lot of the calories, a lot of the food you eat goes to running your brain, because your brain's constantly, right now, it's sending nerve signals back and forth from your eyes just so you can see what you're seeing. And that's constant. It's going all the time. So, and hearing and that sort of thinking. Some of y'all are thinking, I don't know, a few of you maybe not. But the brain is very glucose intensive. And so if you inject some radioactive glucose into a patient, you can take a picture of the brain with a machine that senses the radioactivity. So you got radioactivity coming from the glucose that's moving around in the brain. It's not enough radioactivity to hurt you, but it's enough radioactivity for the PET scanner to pick it up. And the PET scanner will tell you what parts of the brain are active by what has the most radiation going on, what's using the most glucose, you see. So if they say, think of dancing, that might go on back here in the brain, and that would show up as more glucose back here. Or do a math problem, and then they can see that's right here. You see what I'm saying? And they can diagnose problems and such. If you had a stroke, which is a broken blood vessel, then no glucose would be going to a certain part of the brain. And there's just no way without cutting open the head to see that without something like a PET scanner. That interesting? And you've heard of an MRI. An MRI stands for magnetic resonance imaging. And what it does, it takes super powerful magnets in a big machine that vibrate. The magnets kind of switch polarities. It's a big electromagnet, and it switches polarities back and forth. And that vibrates some of the magnetic ions in your body. And vibrates them in such a way where they give off energy, and the machine picks up the energy they're giving off and can draw a picture of the inside of your body, including your brain. And can show, and so the doctor can look at your brain. So again, if there's a tumor or something there, you can see it with an MRI. And so, back in the old days, the only way to look at a brain is to cut open the skull and open it up, or they usually cut a big square out, take that out, and look at it. And to see down deep inside, they couldn't even do that. But now with PET scan and MRI and some of these other things, they can figure out what's going on down there. So it's really amazing technology. Here is a PET scan image. And so here the patient has their eyes open and they say their ears open. I guess they had little things to stop up their ears. So the eyes open and ears open, they're getting high glucose readings from all these areas here. And then the eyes closed and ears open. So compare these two. In the top one, the eyes are open, and in the bottom one, the eyes are closed. Can you make any kind of assumptions about where vision takes place in the brain according to those two pictures? Here the eyes are open and here the eyes are closed. This is the front of the skull and this is the back of the skull. Front of the skull, back of the skull. Where does visual processing occur?
Back and sides.
In the back and in the sides. Yeah, we know that now. Mostly the back. So, you can learn interesting things from this sort of technology. There's an MRI of the brain. And if you had a big tumor or something, You could see that on the MRI. And the doctors could figure out where it is and then go in there and get it out. Oh wait, I had some video footage of a PET scanner. It is like a PET.
The positron emission tomography, or PET scanner, allows a physician to see blood flow to an area such as the brain. The image is formed by the tracking of radioactive isotopes that are introduced into the bloodstream. Computers create an image of the body tissue, converting the energy emitted by the isotopes into a colorful map of activity. A PET scan can be used to diagnose any abnormal physiological activity.
That big machine, that's the PET scanner. You can imagine they're pretty expensive, so, you know, you can't just get one at Walmart. You gotta go to the hospital. Here's the MRI. Whoa!
Whoa!
Maybe not. All right. So you read Mapping the Brain, page 121 and 122. I want to go through a little bit of the tour of the brain, which starts on 123. I'll give you the basic layout here of the brain. Here is the brain, and it's got a bunch of different parts that do different things. You got the big part that is all convoluted, curvy, and has all these dips in it. So it looks like it's all coiled up. That's the cerebrum, is what we call that. The cerebrum is all this part. And that's where all the conscious thought goes on. Everything you're consciously aware of. Memory is spread out through here. Thinking, all the thinking you do is in here. All conscious activity goes on here. And this is the biggest part of the brain. It's huge in humans. If you take a sheep or something like that, though, and you look at a sheep brain, this cerebrum's not nearly as big as a human brain cerebrum. And it's not nearly as folded. The folds increase the surface area to allow more cells to exist in this amount of space. So humans have the largest cerebrum, and it's hugely folded as compared to other animals. Humans can remember more and think better and are the smartest. So we know that this part has to do with thinking and memory and intelligence. Here's the front part of the brain here. That's where they do the lobotomy. The front part of the brain, it's called the frontal cortex. Cortex, by the way, is a word that means outside. So the brain has kind of an outside part that kind of exists on the outside, and then there's a deep inside part that we don't call the cortex. And we'll talk about that a little later. Torre. You late. You're excused. Very nice. So that's the biggest part of the brain. Now there are other parts. This part here is called the brain stem. And the brain stem controls all the unconscious activities. Things that you can do without thinking. Like breathing. Controls breathing and heart rate. And all of the release of, there's the pituitary gland. Have you heard of that gland? That's called the master gland. And it hangs down below the hypothalamus. The hypothalamus controls the pituitary gland. And the pituitary gland controls like the growth of your cells. And the release of other hormones from your thyroid gland and from your adrenal glands. Stuff that you don't have to think about. So this brainstem works without your conscious awareness. There's a couple parts you've probably heard of. This part down here is called the medulla oblongata. Have you ever heard of that? It's just fun words to say, medulla oblongata. That in part, it controls your breathing and heart rate, but it also helps control your emotions. And whether you know it or not, your emotions are partly subconscious. You're not always conscious. You're able to consciously control your emotions. You ever just, you're crying or something like that, and you can't stop it because a lot of it is not under conscious control. Or laughing hysterically, part of your emotions exist in a lot of your emotions exist in your brain stem, which is this part. The pons is another area associated with helping control emotions. It's also a relay center that takes signals coming from the body and sends them to the correct part of the brain. The pons is kind of like the Atlanta of the airplanes, of the airport system. You know how probably pretty much from Atlanta you can go anywhere? So if you want to go anywhere in the world, you go to Atlanta first, and from there you can go anywhere. So all the signals coming from the body come to the pons first, and then the pons sends them to the correct place. The cerebellum is a cool part in the back here. That controls coordination. It's also subconscious. Your cerebellum works without your conscious control. Your cerebellum, for instance, tells you that you put this foot forward here and tells every muscle what to do, and then your cerebellum tells you to do this foot. And your cerebellum, because it's been so highly trained, can keep you balanced and walking. It took you years to learn how to do that, or at least, a couple years to learn how to do it well. When you were a kid, that's what you were practicing. And when you practice something over and over, you teach your cerebellum to do the muscles at the right time. Just to throw a ball, you have to have probably about 50 muscles all working and firing at just the right time to throw that ball in the direction you want to. And if you ever see someone throw a ball who's never practiced throwing, it looks uncoordinated. They don't have the right muscles firing the right way, and the ball doesn't go very far, and it doesn't go in the right direction. And then you watch me throw, and it's just all real smooth, and you're like, wow, he's real coordinated. You're talking about my cerebellum. That's where the coordination happens. They say it takes about 10,000 repetitions to teach your cerebellum to learn something. Then you don't have to think about it. I don't have to think about standing and walking and dancing and throwing and all the stuff I do, hitting a ball about 325. I don't have to think about that. It just happens. I can think of other stuff while I'm sitting here setting up. I can say, what am I going to do tonight after this? Wow, that was great, Coach. Thanks. Sorry, I'm in my own little fantasy up here. But anyway, that's what your cerebellum does. It's a pretty big part of the brain, too. It's hard to control all of your 620 muscles and get them all firing when they should.
You think you swim a golf club 10,000 times?
Oh, yeah. Way more than that. I've played about 6,000 rounds of golf. Calculated that out not too long ago. Each round, I'm hitting it about 67 times. All right, so make sure to read this section. You might want to start reading the next section because it is long, like I say, and I'll continue on that next time.